Hello everyone. Today we are going to study about normal subgroups. In the last lecture we have seen about cosets. So as we all know that cosets are of two types, left cosets and right cosets. So you have a group G and H is a subgroup of G and A is any element of G. Then AH is called the left coset of H and G and HA is called the right coset of H and G. And in the previous lecture we have seen that AH is not equal to HA, that is left coset is not equal to right coset. But there are certain conditions, there are certain situations where left coset is equal to right coset. So those subgroups for which AH is equal to HA for all A in G, those subgroups are of special importance and those subgroups are called normal subgroups. And such subgroups, they have critical importance in group theory. So we are going to study about normal subgroups. The subgroups, a subgroup H such that AH is equal to HA for all A belongs to G. Then that subgroup is called normal subgroups. AH is called the left coset of H in G and HA is called the right coset of H in G. That means we are going to study those subgroup for which left coset is same as right coset. So let us see. So Galois was the first mathematician who recognized such subgroups and they have special importance in group theory. So let us see the formal definition of normal subgroup. A subgroup H of a group G is called a normal subgroup of G if AH is equal to HA for all A belongs to G. And this is the notation of a normal subgroup. If H is a normal subgroup of G, then it is denoted like this. So N is a normal, so if we are saying that H is a normal subgroup of G, then we can also, this definition can also be read like this, that H is a normal subgroup of G if and only if every left coset of H in G is a right coset of H in G. That means there is, you take any left coset, you take a collection of left cosets and you take collection of right cosets of H in G, then every left coset is same as some right coset of H in G. So then in this sentence you may be mistaken, like what mistake you can make, mistake you might make is, just see, H is a normal subgroup of G. It does not mean that AH is equal to HA for A belongs to G and H belongs to H. That means AH is not equal to HA. This may not happen. AH is equal, that is commutativity. This is called commutativity. We are not talking about commutativity. We are saying that AH is equal to, there is equal to H dash A for some other H dash. So normality of H means that if A belongs to G and H belongs to H, then there exists some other H dash in the subgroup such that AH is equal to H dash A. We are not saying that AH is equal to HA. We are saying that AH is equal to H dash A. As in this sentence, we were saying that every left coset of H in G is a right coset of H in G. That means every left coset is equal to some right coset of H in G. So we are not saying that AH is equal to HA, the commutativity. We are saying AH is equal to H dash. Now, when we were proving the lemma, that is the properties of cosets, there we have seen that a left coset is equal to right coset if and only if H is equal to AHA inverse. This is the result, the property of cosets that we have already proved in the previous lecture. Left coset is equal to right coset if and only if H is equal to AH inverse. That means here you have found a necessary and sufficient condition for a subgroup to be a normal subgroup. So H will be a normal subgroup if H is equal to AH, A inverse. So because for a subgroup to be normal, we are saying that AH should be equal to HA, and here we are saying in the property that AH is equal to HA if and only if H is equal to AHA inverse. So if this condition is satisfied, H is equal to AHA inverse, then that H will be a normal subgroup. So now we have this theorem. This is called normal subgroup test. A subgroup H of G is normal in G if and only if XHX inverse is contained in H. This is basically a weaker version of this result. Here what we were saying that AH is equal to HA if and only if H is equal to AHA inverse. That is H, when we are going to prove this, when we have already proved this in the previous video, where here that time we had taken that H is a subset of AHA inverse and AHA inverse is a subset of H. That way we have proved it. So in this normal subgroup test, here we are saying that H is a normal subgroup of G if and only if XHX inverse is contained in H. So this result we have already proved in the previous video when we were studying about the properties of cosets. There we have proved 7 properties of coset. So the proof of this theorem you can see from the previous lecture. That was property number 6 in that video. Now there is another definition of normal subgroup, or you may see different definitions of normal subgroups in different books, but all these definitions are equivalent definition. You can reach to a definition from the other definition and vice versa. So they are all equivalent definitions. One can be obtained from the other. So what is your second definition? Here we are saying that subgroup N of a group G is said to be normal subgroup of G if G and G inverse belongs to capital. So there we were saying that G inverse is equal to H, or one condition was GH is equal to HG. So these all are equivalent. So here we are saying that G and G inverse belongs to capital N. This N is a subgroup, and we say that N is a normal subgroup if this condition is satisfied. Take any element of the group G and any element N of the subgroup N, then check this G and G inverse. If G and G inverse belongs to N, then N is called the normal subgroup. So now we have this example. Let us see this. So it may be observed that every subgroup N of an abelian group G is a normal subgroup of G. So what is an abelian group? Abelian group means where commutativity holds. So AB is equal to BA for all AB belongs to the group. So we are saying that you take any subgroup of an abelian group, then that subgroup is normal subgroup. So basically in normal subgroup we are saying that H is a normal subgroup of G if AH is equal to HA for all A belongs to G, and if G is normal if G is your abelian group, then your AH will be equal to HA. So that will be your normal subgroup. So here let me just explain you. So why we are saying that N is a normal subgroup of G if N is a subgroup of an abelian group? For G belongs to G and N belongs to N, Gn is equal to Ng, because if N belongs to N and N is a subgroup of G, then N belongs to G as well. So you have two members, G and N of capital G, and G is abelian, so Gn is equal to Ng. So from here you can multiply G inverse on the right hand side. So G and G inverse will be equal to N into identity, and N identity will be N. So G and G inverse is equal to N, and N belongs to capital N. So G and G inverse belongs to capital N. That means N is your normal subgroup by your normal subgroup test. So there is another observation. Here we are saying that every subgroup of a cyclic group is normal, and we already know that every subgroup of a cyclic group is abelian, and in this result we have seen that every subgroup of an abelian group is normal. So in a cyclic group every subgroup is abelian, and for every abelian group, all the subgroups are normal. So indirectly, you have that result. So every subgroup of a cyclic group is normal. Now this is example 2. Here we are saying that center of a group is always normal. Center of a group, ZG, if G is a group, then ZG denotes the center of the group. So center of the group we already know. How do we define center of a group? Center of a group means all those elements of the group A belongs to G such that AX is equal to XA for all X belongs to G. G के वो सारे elements, there are some elements of G which are satisfying the commutative property with all the other elements, with all elements of G. So A belongs to G such that AX is equal to XA for all X belongs to G. So this is how we define center of a group. Now in this example, we are saying that center of a group is a normal subgroup. So we have already seen that center of a group is a subgroup of a group. Now we are just going to prove that center of a group is a normal subgroup. So ZG is a subgroup of G. That proof you can see in the previous videos when we were talking about subgroups. So there I have given the proof that ZG is a subgroup of G. Now we are showing that ZG is a normal subgroup of G. So for that, consider any element of the group and any element of the center. So suppose that A belongs to the center and G belongs to the group. So if A belongs to the center of G, that means by definition of ZG, AG is equal to GA for all G belongs to G. So from here, if you multiply it by G inverse on the right hand side, then G inverse is equal to G inverse, that is A into identity, which is your A. So G inverse is equal to A, and A belongs to ZG. That means G inverse belongs to ZG. So this implies that G inverse is a subset of Z because this A was in ZG. So G inverse is contained in Z for all G belongs to G, and hence Z is a normal subgroup of G. So this is how you can prove that center of a group is a normal subgroup. Now here we have given another example. If you have a cyclic group G generated by A and it is of order 12, so A to the power 12 is identity. Then we have found the normal subgroups of G. So this H1 is the subgroup which is generated by A square. So it will be A square, A to the power 4, A to the power 6, A to the power 8, A to the power 10, A to the power 12 will be equal to identity. So these will be the element of H1. H2 is a subgroup of G which is generated by A cube. So these are the elements of H2. A cube, A to the power 6, A to the power 9, then A to the power 12 will be identity. Similarly, H3 is a subgroup which is generated by A to the power 4. So here you will be having three elements, A to the power 4, A to the power 8, and A to the power 12 will be identity. And H4 will be a subgroup which is generated by A to the power 6. So these will be the elements of H4. You can check these all are H1, H2, H3, H4 are normal subgroups of G. So that you can check. You can just take any element of G and take any element. Suppose you are checking H1, that H1 is a normal subgroup of G. Then take an element of G, take an element of H1. Then you just try to satisfy the normal subgroup test. G inverse should belong to H. So that is how you can prove all these four are normal subgroups. Now there is another example. So here n is equal to 1 minus 1. This is a normal subgroup of the multiplicative group. 1 minus 1 iota minus iota. So this we have already seen this group. This is a group under multiplication, complex multiplication. So here this n is a normal subgroup of G. Let us see this example. An means the alternating group of degree n. An is the group of all even permutations of Sn. So An is the set of all even permutations. That is, we have already seen that it forms a subgroup of Sn. So here we are saying that An is a normal subgroup of Sn. So here we have given this note. So 1, 2, this is a permutation, 1, 2, it belongs to Sn, and this 1, 2, 3, this is an even permutation, belong to An. So here 1, 2 into 1, 2, 3, this is not same as 1, 2, 3 into 1, 2, but 1, 2 into 1, 2, 3 is equal to 1, 3, 2. This was 1, 2, 3 and this is 1, 3, 2. 1, 3, 2 into 1, 2. So this is not equal to this. But when you say, when you are taking this as 1, 3, 2, then they are equal. And 1, 3, 2 belong to this An, the even permutation. So normality means that if A belongs to G and H belongs to capital H, here your H is An. So we are saying that if A belongs to G and H belongs to capital H, then there exists some H dash, some other H dash. So here we were saying that AH, we were in the initial pages, we were saying that AH is not equal to HA, but AH is equal to H dash A. There exists some other H dash, कोई दूसरा H dash आपको मिलेगा from the subgroup such that AH will be equal to H dash A. So here that example is given that AH is not equal to HA, but AH is equal to some H dash A. Here H dash is 1, 3, 2 and H is 1, 2, 3. So AH is equal to H dash A. You are getting some other H dash. So AN is a normal subgroup of SN, and here we have just given you an example that normality does not mean that AH is equal to HA. Normality means if you have some H belongs to capital H, then AH will be equal to H dash A. There will exist some other H dash such that AH is equal to H dash A. So that condition that we have tried to explain you that what does normality means. Now here is another example. The GL2R, this group we have already seen in the initial lectures when we were talking about the groups in the initial lectures. So when I have defined the groups, so there we have defined the general linear group GL2R. That means the group where you are taking all the 2 by 2 matrices with real entries and determinant is non-zero. So, and special linear group also we have seen SL2R. SL2R is a subgroup of GL2R. And what was your SL2R? SL2R was all the 2 by 2 matrices with real entries and determinant was 1. Here determinant was non-zero. Here determinant is 1. So this is a subgroup of GL2R. So here we are saying that SL2R is a normal subgroup of GL2R. So that you can verify from the normal subgroup test. Take any element of SL2R, any element of GL2R and prove that G inverse belongs to SL2R. So that you can do, you have to just multiply the permutations, multiply the matrices. So then you can prove that SL2R is a normal subgroup of GL2R. So in this today's lecture, I have given you some knowledge about normal subgroups. So normal subgroups are basically those subgroups for which left cosets are equal to right cosets. AH is equal to HA for all A belongs to G. And that we have seen some normal subgroup test also, definition, some equivalent definitions, and uh, all the subgroups of cyclic groups, they are normal that we have seen. So these are some of the important results related to normal subgroups. So in the next video, I will be giving you some more examples of normal subgroups, how to prove that a particular subgroup is a normal subgroup or not. So those examples I will explain in the next lecture. Till then, bye-bye.